title is Manhattan Distances, Metric Transforms, and Kernels. And this is joint work with Gary Miller, my advisor at Carnegie Mellon, Shyam Narayanan, a student at MIT, and Mark Selke, a student at Stanford. So before we get into this talk, let's just briefly define what a Manhattan distance is. It's also known as a taxicab distance or an L1 distance. But the way you define it is given two coordinates. You'll subtract each component, take the absolute value, and add them, as seen here. Of course, this example shown generalizes into multiple dimensions. So the way this talk is organized will actually be very interactive, and I strongly encourage participation. First, I'm going to be going over a core puzzle that guides our talk. Then I'm going to be giving background about it, showing that it's not just a cute math puzzle, but actually has deep links to a lot of areas of mathematics and computer science. Finally, I'll be going over some of the background tools and giving an outline of the proof of our core puzzle. And finally, I will be giving a full proof of our core puzzle. So by the end of this talk, you should actually understand how we're going to solve the core puzzle I'm about to present. So the motivating puzzle is as follows. Let's say you have n points in any dimension at any n, and you compute the n choose 2 Manhattan or L1 distances between each pair of points. Then you do something crazy, like raise each distance to the 1/2 power. And here 1/2 can really be replaced by any constant between 0 and 1. But let's stick with 1/2 for now. I claim that the result is always a Manhattan distance. This means I can find n new points in arbitrary dimension, such that the distances between these points are our old distances raised to the 1/2 power. And the question that will guide the entirety of this talk is, why should something like this be true? And moreover, in general, what functions have this property? So I'm actually going to give it a simple example, which is let's just try it for 3 points on a line at 0, 1, and 2. So I actually want to give everybody 1 or 2 minutes to think about this themselves and try to come up with the new points that realize this Manhattan distance. What we're going to do is take all n choose 2 distances, raise them to the 1/2 power. And I want you to find the Manhattan embedding that realizes those new distances. So I'll give everybody about 1.5 minutes to think about this. And the purpose of this exercise, besides for just thinking about it, is to give everybody a chance to ask questions in case they're confused about the setup. So 1.5 minutes. And again, my talk will be interactive, so it will be full of these little pauses and cute little puzzles. And again, if you have the questions about the setup, feel free to ask. If you don't want your question on YouTube, feel free to ask via the Zoom chat. Okay, well, hopefully that was enough for people to get their fingers at least a little bit dirty. Some of you may have solved it, some of you maybe not quite, which is fine. But the purpose is just so we can understand via a simple example what this question is all about. So I'm going to present the solution real quick. We're going to compute all 3 choose 2 pairwise distances. They are 1, 1, and 2. And when you raise their distance to the 1/2 power, you get 1, 1, and square root of 2. Now I want to find 3 points whose Manhattan distances are these 3 distances. And it turns out, I'm just going to write it here, A, B, and C as follows. You can quickly verify for yourself that the distance between A and B is 1, the L1 distance, that is. The Manhattan or L1 distance between B and C is 1, and the Manhattan distance between A and C is the square root of 2. So I'd like to pause here for about 15 seconds, just so people can see that this is actually realizes the distances we want. And I'll also take any questions that people have right now. Oops. Okay, well, I'm assuming the silence means people are roughly on board with this. And I'm going to give you a quick definition. So the definition here is that if function f equals square root of x, we say sends Manhattan distances to Manhattan distances if it has the property we described. For any endpoints in d dimensions, you apply f termwise to each distance, and you get a resulting Manhattan distance back. That means f sends Manhattan distances to Manhattan distances. And let me briefly outline the mysteries of our talk that we will have the answer to by the end. First of all, how does this question on Manhattan distances relate to computer science? Is this just a cute, fun little puzzle in mathematics? Second, why does the square root of x send Manhattan distances to Manhattan distances? And by the end of this talk, we'll have a nearly complete full proof of this fact. So let's briefly go into why this puzzle relates to computer science theory. And the big picture question is, for a general metric space M1 and a general metric space M2, what functions send M1 to M2? Now, it turns out that the study of this question is actually quite old, in the case when M1 and M2 are both Euclidean distances. So in this case, it was known that the square root of x has this property. And this was shown by Schoenberg and John von Neumann in a series of papers from Annals of Math, 1937, all the way to some papers in 1942. And it turns out that their study of this, mostly done by Schoenberg, von Neumann is a small part of this work, it turns out that the study of this is essential to the study of a lot of areas of mathematics, including harmonic analysis of semigroups, reproducing kernel Hilbert spaces, and so forth. It's not important what those are, but the key point is those are very, very large areas of mathematics that questions like this actually spawned. But let's focus on how this puzzle relates to computer science theory. So it turns out that this kind of results, when M1 and M2 are Euclidean distances, is integral in a lot of embedding theory. So recently, Andoni, Krautgamer, and Rajenstein showed in Stock 2015 that sketching and embedding of norms are equivalent. And key to their proof is the fact that x to the 1/2 send Euclidean distances to Euclidean distances. Again, this is a completely non-obvious fact. Another result from SOTA 2020 by myself, Gary Miller, and Donald Sheehy was how to exactly compute a certain type of geodesic metric inspired from machine learning. Now, the key point here again is just that this overall question, in the case when you have Euclidean distances to Euclidean distances, is the progenitor of large areas of mathematics, but is also a core tool in embedding theory and the forefronts of theoretical computer science. And again, what our work addresses is what happens when you just replace Euclidean norms with other norms, like the Manhattan norm or the L1 norm. Now, I should say one brief other large application. How does our puzzle, on x to the 1/2, relate to machine learning? And it turns out there's actually a very deep connection between this kind of topic and machine learning. So our puzzle is deeply related to something called kernels, positive definite kernels, which is one of the core tools in machine learning. It was introduced by Smola in 1996. And it's been cited over 10,000 times since. It's actually deep in the loop of a lot of even modern neural networks. But what kernels are not so important. The founding question of kernel theory is the following. For what functions f, can I have a function g such that when I apply f to the Euclidean distance between x and y, this is equal to an inner product of g of x and g of y for all x and y in a Hilbert space. So I'll give everybody about 20 seconds to briefly digest what this question is asking. Basically, it's asking for what functions send Euclidean distances to a valid inner product. And yeah. So an example of such a function is e to the negative x squared. This is known as the Gaussian kernel, one of the most popular kernels in machine learning literature. So again, just a quick 10-second pause so people can digest the definition a little. Okay, well, it turns out this question is the center of everything in kernels, but we're just asking a simple question. What happens if we replace the 2 norm with the 1 norm? And this question, if you replace the 2 norm with the 1 norm, is deeply related to the puzzle we gave at the beginning. And in fact, we solve this question in the paper. We fully classify all such functions f, such that if you apply f to the Manhattan distance between 2 points, you get an inner product. This is outside the scope of the talk. But the core techniques we use to do this part are exactly the same as the techniques we'll show to solve our core puzzle, which we showed at the beginning. And I should mention that one-norm kernels are actually pretty widely used in practice. In particular, they're sort of the gold standard for how you do machine learning and quantum or molecular chemistry. So if you're trying to predict the energy of formation between two chemicals using machine learning, it turns out that using one norm or Manhattan distance kernels are widely used in that setting. And thus, our work about classifying all such Manhattan distance kernels can be applied to these areas of machine learning. So that's a brief summary of how we relate our work to computer science. It's an extension of a classical embedding theorem from Schoenberg and von Neumann used everywhere. And it also deeply relates to the central question in all of kernel theory. Now let's briefly state what our work proves. So we provide a simpler self-contained proof that something called a Bernstein function sends Manhattan distances to Manhattan distances. Don't worry about what Bernstein means. Just know that the square root of x is an example of a Bernstein function. This was actually known before, but the proof was a little bit more intricate. This is the result of Schoenberg in 37 and Aswad in 1980. Now, our work is that only Bernstein functions have this property. And this, to our knowledge, is new. We also fully classify functions that send Manhattan distances to inner products, as mentioned on the previous slide. Before the course of this talk, we will simply focus on the first point. This will build all the core machinery in our paper that can later be used to prove the other 2 points. So let's briefly summarize the takeaways from the talk here on out. Why does square root of x send Manhattan distances and Manhattan distances? A full proof. And a deeper understanding of the background tools, which I think are actually quite interesting. First, Manhattan distances. Second, a criterion for how you determine whether a distance, if I just gave you and choose 2 distances, how do you know if this is a Euclidean distance between endpoints? Equivalently, how do you know if it's a squared Euclidean distance between endpoints? And finally, there's a key central part where we use Walsh-Hadamard transforms and group representation theory. Very simple group representation theory, mind you. It will be accessible to people who even don't have a group theory background. I should emphasize that all the background tools are not like something that I developed. These have been known in the literature for a while. So the way that this talk is going to go is I'm going to go through a deep dive through the background. Then I'm going to give an outline of the proof of our core puzzle. And then I'm going to give you a proof of the core puzzle. But I should just say, as a little taster for what's to come, this talk and the proof of our core puzzle is actually a question about symmetry groups of matrices and how, when you apply a symmetry group to a matrix with symmetries, you have very predictable eigenvectors and eigenvalues. So underneath this question that seems to be all about metrics and Manhattan distances, there is a question about group theory, symmetry, and matrix eigenvectors. So that's a little bit of a teaser of what's to come. But for now, we're going to dive into the background to give people a greater appreciation of the tools, and then we're going to proceed with the proof. So once again, Manhattan distances. I think I've described this twice already, so I'll skip this slide. But let me give you a short puzzle on Manhattan distances that should be accessible to anyone regardless of background, and is also a very key lemma in our proof. So I want you to show that any 3-point Manhattan metric is equivalent to a Manhattan metric on 3 corners of a high-dimensional hyperbox. And by hyperbox, I just mean a general rectangle, like a rectangle in d dimensions. And I'll actually give everybody a couple minutes to think about this. If you happen to see this right away, try it for 4 points or even n points. So I'll just pause for a couple minutes to give people time to think and really grapple with this problem. And again, for people who might have trickled in a bit late, right now I'm simply going through the background tools we need to prove our core puzzle on Manhattan distances, which you can find in my talk abstract. And again, feel free to use this time while grappling with this question to ask any questions you might have about the setup. And again, I just want to emphasize that this puzzle is deep in the loop of our proof. So it's worth spending a little bit of time pausing here and thinking about. Okay, I think that's enough time so people can at least have tried a couple of things, even if you didn't come up with a full proof. But I'd like to ask the audience, can anyone give me like a proof of this fact that I've stated here? And feel free to just jump in or type something via the chat.
Not quite a proof, but I'm going to transformation. I want to take the 2 points that are closer to each other and just imagine preserving those in the plane. And I want to take a point that's further away and put it above the point it's closer to at the appropriate distance. And so basically, I want the fact that the further point is equal to some distance plus the distance to the closer point. And I think that preserves things.
Mm-hmm. And why are they on a corner of a box in this construction?
They're in the corner of a box because the 2 points define a square, and I move the other one to have the same xy coordinates plus some z amount. Mm-hmm. I guess this would be easier with a drawing.
Oh, yes. Yeah, I apologize that I haven't quite figured out how to do drawings here. But I think your box in this case is 3-dimensional. Is that correct?
Yes.
Yes. Yes, something like this argument will definitely work. So thank you for volunteering. I do have a couple diagrams prepared, so hopefully those will be a little easier to follow, but I do think that will work. So I'm just going to give a simple example in 2 dimensions, but this will generalize to arbitrary dimensions. So let's say I have points A, B, and C in 2 dimensions. What I'm basically going to do is I'm going to extract the x coordinates and the y coordinates, embed those separately, and then concatenate the embeddings. But if in case you didn't follow that, let's just try and do that here with an example. So I'm going to project onto the x and y coordinates, as mentioned. And now, when I project, it sort of splits up the x and y coordinates into different intervals. And I'm going to do the embedding as follows. And I'm going to use more dimensions than you need, because this isn't about conserving dimensions. But let A prime be the point A00, D00. And let B prime be the point ABC, DE0. Well, how are these generated? Well, when you drop A to the y-axis, it only covers that interval little a. And when you drop big A to the x-axis, it only covers that interval little d. So you write A00, D00. Meanwhile, with point B, when you drop it to the y-axis, it covers the interval little a, little b, and little c. But when you drop it to the x-axis, it only covers little d and little e. So this point gets mapped to ABC, DE0. Can anyone guess what C will get mapped to in this construction I'm drawing here? And feel free to just shout it out. Anyone?
AB0, DEF.
That's right. So because it covers, AB on the y-axis, it'll just cover AB0. And when you drop it to the x, it covers DEF. So you have DEF next. And I'll give you like 10 seconds or so just to verify here. Well, first of all, these are corners of a hyperbox. The hyperbox dimensions are A, B, C, D, E, F. The second thing I want you to verify is that the Manhattan distance between A prime and B prime is the same as the Manhattan distance between A and B. And of course, you can verify this for any other pairs. So I'll just give you like 5 or so seconds to like look at this and convince yourself that this is the case. Okay, and this construction will generalize to arbitrary dimensions. So to just summarize what briefly happened, what we showed is that if you have n points in Manhattan distance, there exists some high-dimensional hyperbox or a high-dimensional rectangle, such that the Manhattan distances between those corners of the rectangle are equivalent to your original Manhattan distances. Next, we'll be going over a famous result of Schoenberg, which is how to determine whether a given distance, if I give you n choose 2 distances, embeds into squared Euclidean distance. And again, these tools are just essential to building up an understanding for how we prove our core results. So this, I won't actually prove for you why it works, but I'll just give you the criterion. So let's say I give you a distance d on a set x1 through xn. It is a squared Euclidean distance, that just means the Euclidean distance squared, if and only if the matrix where the ijth entry is the distance between xi and xj has the property that x transpose dx is less than or equal to 0 for all x orthogonal to the all ones vector. Now, this is a fairly complicated criterion, but this is known in the literature as being a negative type matrix. And I should emphasize the reason we're talking about squared Euclidean distances instead of just Euclidean distances is that the theorems are just a little bit easier to state when we talk about embedding into squared Euclidean distances. So here, we're assuming that the distance between a point and itself is 0, and the distance is symmetric. But we're not necessarily assuming the metric property. And indeed, squared Euclidean distances don't necessarily obey the metric property. So again, we're just trying to find out a criterion for when a set of distances embeds into squared Euclidean distance. Now, this is a fairly complicated criterion, and I don't expect you to understand it here. But let's give a simpler criterion for how we can test for this. So let's say D is a symmetric matrix. And D has an eigenvector, which is the all ones eigenvector. And all other eigenvectors have negative eigenvalue. This is a very strong assumption. This rarely happens with distances. But let's assume that this is the case for now. Then I claim that D is of negative type. X transpose dx is less than or equal to 0 for all x orthogonal to the all ones vector. Why would this be true? And I'll give everybody about 30 seconds to think about this. Again, this is a great time to ask questions in case you got lost. And again, just to summarize where we are, we're knee-deep in trying to show a criterion for when a set of distances is embeddable into Euclidean distance, aka their Euclidean distance. And it turns out a criterion is when you put them into a matrix, they have this nice little property. Don't worry, how this all relates to our core puzzle will come together very soon. Okay, anyone want to give a volunteer for why this assertion I made on the slide is true? Feel free to just jump in. And also feel free to ask questions in the chat in case this doesn't quite make sense to you. I should emphasize the reason I'm going fairly slow and pausing through all this is that I am going through a number of fairly intricate topics. And I do want to, make sure that the audience is sort of engaged and sort of following along because I know it's very easy to get lost during these detail-heavy theory talks. So yeah, feel free to jump in, explaining why this, this claim I made could possibly be true. Or maybe feel free to jump in saying, maybe something here doesn't make sense. Okay, well, I'll just go through it. I mean, this is actually fairly simple. You know, if your matrix D has an eigenvector of the all ones and all of the other eigenvectors have negative eigenvalue, well, you know D is symmetric, so all the eigenvectors are orthonormal. And so, you know, X transpose dx, or X, if X is orthogonal to the all ones vector, is just some linear combination of the other eigenvectors. Let's skip a couple examples, but let me just overview what that was all about. So a sufficient criterion for showing if a distance is a squared Euclidean distance, and you can understand this slide even if you got lost in the rest, is if you have a distance, fill the matrix D with the distance between xi and xj. Let's suppose, by magic, that D has the all ones vector as an eigenvector, and all the other eigenvalues of D are negative. Then Dij embeds into squared Euclidean distance. Of course, there are many squared Euclidean distances that don't have these magic matrix properties we described, but it turns out for our proof, this criterion is enough. So what we've done is established a criterion for if you give me a set of distances and they happen to have the magic properties in these 2 bullet points, how do I know if the distance is a squared Euclidean distance? Great. So let's go back to the overall puzzle. If I apply the square root function to a set of Manhattan distances, I will always get a set of Manhattan distances back. And let's go to a quick proof outline. Without loss of generality, let's assume that the Manhattan distances are the full set of corners on some hyperbox. Okay? And we saw from the previous puzzle that it's okay to assume this. Then we will show that the square root of x sends these distances, these Manhattan distances. If I apply them to each n choose 2 of them, I will get back a squared Euclidean distance. And I'll see that by testing the criterion that I just showed. But moreover, it'll happen that these squared Euclidean distances are squared Euclidean distances on a hyperbox. And I claim that squared Euclidean distances on a hyperbox are just Manhattan distances. Now, this is a fact that you can verify pretty easily through the Pythagorean theorem. So that'll be a puzzle I'll leave for you for after this lecture. You know, why do squared Euclidean distances on a hyperbox? Why should they be Manhattan distances? So let's go through the outline, what we're going to do now. I gave you the rough outline of the proof, and now I'm going to go through step by step. Oh, and by the way, actually, I'm going to go back to the outline here real quick and just give everybody a quick moment to stare at this outline and convince yourself that if I prove every single step of this, then I've shown that x to the 1/2 sends Manhattan distances to Manhattan distances. So I'll give about 10 seconds to look at this slide. Again, I should explain I like going fairly slowly because this slide is very important for what we're about to do. Okay, and if you have any questions, of course, feel free to ask or feel free to jump in the comment section. So we're going to show the first part of this, which is x to the 1/2 sends Manhattan distances on a box to squared Euclidean distances. And we're going to do a proof by example using a 2-dimensional box. Now, a proof by example isn't a real proof, but it turns out what we do here will generalize, in fact, to arbitrary dimension. So let's say we have a rectangle with side lengths a and b, and your function f is equal to square root of x. Now, I'm just going to lay down a couple coordinates. And it turns out that if we want the matrix D, where I put the ijth entry as the distance between xi and xj, it's going to look something like this. What I did was compute the Manhattan distance between every pair of points, and then apply function f. So just take my word for it that this is the matrix you get. And I claim that the all ones vector is an eigenvector of D. And you can see this pretty clearly because the row sums of the row sums of every row in this matrix are the same. And I claim all the other eigenvectors of D are negative or 0. And recall that these 2 criterion were something we've seen before. Question is, why? Why should all the other eigenvector values of D be negative or 0 when we have this setup? Well, let's take a quick look. First of all, we know that the all ones vector is an eigenvalue, or an eigenvector, and I claim that the other eigenvectors of D are the columns of the 2 by 2 Hadamard matrix, which I've shown below, excluding the constant scaling factor. And I claim this is true no matter what f is. There is no restriction on f whatsoever. For any f that I can give you, all the eigenvectors of D are the columns of these Hadamard matrices. And you can verify this yourself by computation, but I'll skip that for now. But here's where I want to say there's a secret use of very simple group representation theory. Boxes, if you think of high-dimensional rectangles, they're symmetric under axial reflection. And any permutation matrix corresponding to axial reflection will sort of preserve the Manhattan distances between points. And because there's this group symmetry underlying our object, which is the high-dimensional hyperbox, there will be a group symmetry of this matrix. And because this matrix has the appropriate symmetry, it turns out that no matter what the function f is, you will always have the symmetry, and you will always have a predictable set of eigenvectors. This is a secret use of representation theory. Group representation theory is in fact much more complicated than this, but this is a very simple application of ideas from that area. So the key takeaway here is if I have a distance matrix D that comes from a structured set of points with a simple group symmetry, in this case axial reflection, then the eigenstructure of D is actually very predictable, no matter what functions f I apply termwise to it. So again, we're just trying to show that D is a negative type matrix to show that our distances are squared Euclidean distances. And I'll just show this by direct computation. So let's try to compute the eigenvalue lambda corresponding to the eigenvector v equals 1 minus 1, 1 minus 1. This is one of the columns of the Hadamard matrix. So you know it satisfies d times that vector is equal to lambda times that vector. And I'll spare you the computation. It's a very simple thing you can do. But this can just be calculated by evaluating the first row of d times v. And that's equal to negative f of a plus f of b minus f of a plus b. Now, by the fundamental theorem of calculus, it's equal to this kind of interesting integral formula over here. So this is one of the eigenvalues of the matrix D. And I claim this will always be negative, or at least not positive. And my question for you is, why? What property of f makes this last expression always negative, no matter what a and b are? And again, I'll pause just a little bit here to give people a little bit of time to think about it. If you have an idea, feel free to jump in. And again, just the overall framing of what we're doing. We're knee-deep in showing that x to the 1/2 sends Manhattan distances on a box, on corners of a box, to squared Euclidean distance. And we're showing that because there was some cute matrix criterion that had to do with checking whether eigenvalues were negative. Well, it turns out that this will always be negative because the derivative of the square root of x is like 1 over the square root of x. That's always positive for x greater than 0. So if you integrate a positive thing and make it negative, you will get a negative number. And of course, you could have shown more directly that the quantity, the eigenvalue was negative. Now I'm going to do this computation again for a slightly more interesting row of the Hadamard matrix, which is the 1, -1, -1, 1 row. Turns out, just by computation, the eigenvalue is equal to f of a plus f of b minus f of a plus b. And that's equal to the double integral of f double derivative x plus y. And if you look at what this integral is, it's basically the integral of the double derivative over the a by b rectangle. And why is this always going to be negative? Well, what's the double derivative of f? F is equal to square root. It's equal to some scalar times negative x to the -3/2. So basically the double derivative of f is always going to be a negative number. So if I integrate that over the bounds of my rectangle, that's still going to be a negative number. So what we basically showed is that when we have a 2 by 2 rectangle generated by placing the Manhattan distance in the between I and j, the ij corner, into the ijth entry, and then applying a function f, this matrix has eigenvector, one of the eigenvectors is all 1, and all the other eigenvalues are negative. This means it's a negative type matrix. And in fact, as mentioned before, this is equivalent to the distance being a squared Euclidean distance. So what we showed is that at least for a two-dimensional rectangle, the corners of a two-dimensional rectangle, x to the 1/2 sends Manhattan distances to squared Euclidean distances. And even if you didn't understand any of that, the key point is that we just had some matrix criterion, and this matrix had a very nice set of eigenvectors because it has some symmetry. Well, what property of x to the 1/2 did we use? We used the fact that its first derivative was positive and its second derivative was negative. Now, in general, you actually need to use more derivatives. So the general property is that the first derivative should be positive, the second should be negative, the third should be positive, the fourth should be negative, and so forth. And when I say positive and negative, I include 0 here. So once you have, basically every derivative must alternate in sign after the first derivative. And such a function is known as a Bernstein function. Bernstein functions are deeply related to large areas of mathematics, but we won't worry about that too much here. Just know that the key property we used is that the derivatives after the first derivative alternate in sign for all positive x. So this shows a weaker result than the one we wanted to. What we showed is that if you take the corners of a box in whatever dimension and apply square root of x, this sends this Manhattan distance to a squared Euclidean distance. But that's not enough. I promised you that it would send Manhattan distance to squared Euclidean distance on a box, which is equivalent to Manhattan distance. So how do we show this? Well, it turns out we can show this by backing out the actual embedding of points. So it turns out that if I give you a set of squared Euclidean distances, there's been a long established criterion for how I can find the set of points that realize the squared Euclidean distance. And it turns out that when we do that, these points will lie very neatly on a box. And this once again has to do with the structure of the Hadamard transform, which relates to the symmetry group of the box. So what is the actual embedding? Well, at a very rough level, without going through much details, let's suppose that our eigenvalues of this matrix D that we were looking at before are lambda 2, lambda 3, and lambda 4. As mentioned before, these are all negative or non-positive, besides for the all ones vector, which we're not looking at. The actual embedding is something that the rows of this matrix over here. Okay, so because each lambda is negative, every item under the square root is positive, so you don't have any imaginary numbers floating around here. But where did this matrix come from? Well, where did this embedding come from? If you look at this matrix, each column is a Hadamard matrix, or a Hadamard vector, a column of the Hadamard matrix, scaled by the square root of a negative eigenvector, a value. So again, this is the actual embedding. Where did this come from? Just look at each column. It's a scalar copy of one of the vectors in our Hadamard matrix. And it turns out these are the corners of a box with side lengths negative lambda 2 square rooted, negative lambda 3 square rooted, and negative lambda 4 square rooted. Here I ignored the constant scaling factor. But the key point is when you actually back out the embedding of these distances, you get a very, very nice structure. In fact, these new points that realize the Manhattan distances we want live on a high dimensional box, and the dimension of the box are actually just the square root of the negative eigenvalues. Now, the last part of my talk will be devoted to showing this. This part of the talk will be going a little bit faster, so don't worry if you don't understand anything from here. I'm just trying to give you a rough overview of how it works. Well, let's say you have your squared Euclidean matrix D. How am I going to back out the actual embedding? It turns out that you can find a matrix of dot products, which I'll call M, by computing negative pi d pi over 2. And here pi is the projection matrix off the all ones vector. Again, basically, if I have a bunch of points and I have their squared Euclidean matrix, I can figure out what the dot products between each pair of points is by computing the following matrix. It's well known. It's an exercise for the reader. It actually has a beautiful proof. It's not one of those ugly results. It's been known since Schoenberg in 1935. Now, it turns out that if you have a matrix P, such that PP transpose is equal to our matrix of dot products, the matrix P has row vectors which realize our squared Euclidean distance D. Once again, this is a known fact and an exercise for a reader. What is the key point of this slide? If I give you a set of distances, which I know are squared Euclidean distances, I can back out the embedding by first applying some kind of projection transform and then doing a factorization of my matrix. It turns out that if you try this, and I'm actually going to skip the details here, it's not so important, but it's actually not that hard to do. If you try this on our matrix D, you can write D in the classical form, which you see below. And M will also have a very predictable form. And one reason it has a very predictable form is that this matrix D has the all-1 vector as an eigenvector. It's very crucial to the heart of our proof. Turns out you can then factorize it once you have the structure of M, and you get that your embedding P is exactly the matrix that I showed you before. Like I said, the rows of P are on the corner of the box. Now, don't worry too much if you didn't understand this last portion. Just know that at a high level, our matrix was so structured that when you compute the embedding of points, realizing those distances as a squared Euclidean distance, you get something that looks actually quite nice in terms of the eigenvalues of your matrix. So again, let's just go through a proof recap. I know that last part was a little bit fast. Without loss of generality, we assume that the Manhattan distances come from the full set of corners on some hyperbox. Again, this goes back to the puzzle that we spent some time on in the middle of this lecture. Next, we showed that x to the 1/2 sent these distances to squared Euclidean distances. Moreover, it sent them to squared Euclidean distances on a hyperbox. Finally, we showed that squared Euclidean distances on a hyperbox are Manhattan distances. Well, we didn't actually show this, but I claim this is actually a pretty simple exercise. Therefore, when you put it all together, the square root of x sends Manhattan distances to Manhattan distances. And that's the recap here. But underlying all this was a statement about symmetry groups and on matrices and eigenvectors having very nice structure when your matrix has a certain particular structure. That's the high-level takeaway I want everybody to have. So briefly, what we proved, or what we can extend this proof to show, is that if you take any set of Manhattan distances and apply a Bernstein function, again, a Bernstein function is just one whose derivative sign alternates after the first. Once you apply a Bernstein function to any Manhattan distances, you will always get a Manhattan distance back. So let me just give you a couple examples of Bernstein functions, which include the square root of x. So x to the s for any s between 0 and 1 is a Bernstein function. So is 1 minus e to the negative tx for any t greater than 0. This fact is deeply related to Gaussian kernels, which was mentioned at the beginning. We've listed a couple more functions here, but you can just verify by taking successive derivatives that their sign will alternate. It's actually sort of a cool exercise to do. You can just try it for like x to the 1/2. Also, any positive linear combinations of the above should also work. So before I close the talk, I'd actually like to give a couple of open questions. So what did we prove in this talk? Prove, quote unquote, on a 2-dimensional rectangle. But what we proved in this talk was that if I have any set of Manhattan distances, endpoints, and I take the Manhattan distances and apply a function f, well, if my function f was Bernstein, then I will always get a set of Manhattan distances back. That's what we showed. In our paper, what we showed is no functions besides Bernstein functions have this property. So a function has this property if and only if it is Bernstein. Now, what's an extension to this problem? Well, there are many, many natural extensions. Let's say I take any metric space M1 and any metric space M2. And I want to know exactly what are all the functions that send metric space M1 to metric space M2. Well, from what I can tell, this question is wide, wide open. If you take, say, if you want to consider functions that send L3 to L3, I don't think there has been significant work done on that. If you want to take functions that send, effective resistances to L2, well, we actually do have an unpublished paper that addresses that problem. But there are all sorts of different questions you can ask. And in some unpublished work we've done, we've examined what happens when you ask for functions that send effective resistance distances. This is some object from electrical network theory to Euclidean distance and so forth. And it turns out that if you do something like that, suddenly your proof techniques evolve to deal with infinite walks on infinite networks, effective resistance on infinite networks, fractional calculus, and all sorts of interesting things. So we have a lot of very cool unpublished work relating this general idea in metric transforms, which is what functions f send metric M1 to M2. And I should also mention, just as one last piece, if I ask a question like what functions f send, say, icosahedrons to squared Euclidean distance, the techniques that we developed here will also work there, because an icosahedron is an object with a lot of group symmetry. So any object, any M1 with a lot of group symmetry, whether it's a crystal system or whether it's icosahedron or a a triangular prism or anything with high group symmetry, you should in principle be able to apply these techniques for and get a full classification. So that's roughly the end of my talk and the end of my time here. I'll open up the floor for questions, and I'd like to thank everybody for coming out for this talk today. I did something a little experimental by giving people, time to think about these puzzles in the middle. And even if you don't have any questions, I would love to hear some kind of feedback on that. Thank you very much, and thank you very much for having me today.